Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. We continue in this lecture going through the complex zeros and the fundamental theorem of calculus, fundamental theorem of algebra. There is a fundamental theorem of calculus, by the way, but yeah, we continue through with the fundamental theorem of algebra. And we had just finished the complete factorization theorem, and we've written down the fundamental theorem of algebra as well. And this video introduces two last big theorems that really help, and we kind of seen a preview of this already. So the zeros theorem says that every polynomial of degree n, which is greater than or equal to 1, so it's not a 0-degree polynomial, has exactly n complex value zeros, provided that a zero of multiplicity k is counted k times. The proof of this falls out very quickly from the complete factorization theorem and the factor theorem. The complete factorization theorem allows us to say, well, if we have a nth degree polynomial, then we can factor that into the product of n linear factors. And then the factor theorem says, well, if you have a polynomial and it has these factors, then those c sub i's in there, c sub 1, c sub 2, and so on and so forth, are all zeros of your polynomial. And I've written that right there. The thing that kind of attaches to this theorem, the thing that we want to really focus in on, is this last little statement after the comma. This piece right here, provided that a zero of multiplicity k is counted k times. Well, the complete factorization theorem never stated that those c sub i's, like c1, c2, and so on and so forth, it never stated that those had to be different. So ci and ci plus 1 and ci plus 2 and so on and so forth could be the same. So I will write that down, but that still means that you have n linear factors. Yes, some of them might get double counted, some of them might have multiplicity greater than 1. So if C1 was, let's just pretend for this argument, I'm not going to keep those in this proof, by the way, but let's just say that those two are 1s, then you'd have x minus 1 squared. You still have those two factors, and so you still have that zero of multiplicity 2, and so you still have n zeros altogether. So this theorem is more of just a formalized statement of something we already kind of knew. So it's not really that big of a deal. I mean, it is a big deal. It's a very important theorem. So now you know that if I hand you a polynomial and it's 20th degree, it should have 20 zeros. That's it. If you have a 17th degree polynomial, you will have 17 zeros. Some of them might be complex valued zeros with imaginary numbers, like, with non-real parts to them or imaginary parts to them, but that's just the fact of the matter. So I know I'm notorious to have these by having these large examples, and here's yet another one, right? A massive polynomial. Let's just see if we could do this in a short amount of time, really to practice skills. Actually, you know what I think you should do? Pause the video and try it out. All right, so I've written down the constant and the lead coefficient, or the leading coefficient. Now I'm going to write down some candidates. I'm going to zoom in for that. Notice I only wrote down 2. The reason why I only wrote down 2 groups of candidates is I really like to hover around the number 1 for a little bit, just because those are fast numbers. Once you start getting to numbers like 5 and 8, things get a little bit large and out of control. And so I'd like to keep my numbers as low as possible initially. All right, so we get that 1 is a 0. And now I'm going to go ahead and I'm not going to write anything else down. I'm just going to point an arrow at that to let myself know that that works. And then I'll try 1 again. And again, you see that we get another one that works. So we're slowly reducing this down. Let me try 1 again. All right, so that didn't work. Now we have to switch gears, and luckily I can erase. And by the way, I was just checking my work. There's just there is a mistake in here, but still doesn't really change anything. That's a 20. That would be a 37 and then 37. Still doesn't change anything. It doesn't work. So I have the luck of having a computer in front of me, a tablet, so I can erase that line and now try the -1. So here I go. Nice. So we get down that far. So now we have yet another 0. Let's go ahead and try that -1 yet again. All right. So again, getting lucky here. And look how, well, it's not small, but it's getting less, right? Started 10th degree when we went to, let's see, 9th, 8th, 7th, 6th. We're at a 6th degree polynomial, I think. So let's go ahead and continue forward. I'm going to try that -1 yet again. Why not? All right. I really like this. This is actually a lot better than I thought it would be, and I made this example. All right. So let's go ahead and try that -1 yet again. No whammy, no whammy. Now at this point, I'm just going to say that this is ridiculously high, so I know immediately it's not going to work there. So I'm going to switch gears. Let's go ahead and we've done pretty well so far, actually. That happened very quickly. So the plus and minus ones are done. I will go ahead and get rid of those. Maybe I'll just cross them out. Not that they're bad. We've just finished with them. Now I'm going to try the plus or minus 1/2. And again, I'm going to do the same thing where I erase this lower list of numbers, and then I'll just use that same space. All right, here we go. Remember, if the fractions get bad, I will stop. And check that out. Not bad. Pretty excited about this one. All right, now we're going to go ahead and do half again. And lo and behold, we get yet another successful 0. So that's really good. Well, hey, we haven't exhausted 1/2 yet. Let's go ahead and just try it again. No whammy, no whammy. Let's see if we can make this work again. Actually, at this point, you're almost able to. In fact, I think, nope, you're almost able to factor. If you look at these, that would be 8x cubed minus 20x squared plus 48x minus 20. It looks like that would factor, and it might. But if I can test 1/2 again, I'd like to, just really quickly. And lo and behold, really, really awesome. And by the way, this very last one is a trinomial. 8x squared minus 16x plus 40. Something that looked terrible from the beginning actually wasn't too bad. So P of x, we'll go ahead and write this out. Remember, 1 ends up being a 0 of multiplicity 2. -1, maybe write that there. -1 is a 0 of multiplicity 3. 1/2 so far is a 0 of multiplicity 3. I say so far because I haven't really factored that last trinomial, but we'll go ahead and factor that last trinomial actually. So I'm going to grab this guy and just say we have an 8x squared minus 16x plus 40 left over. Of course, all of those you could factor an 8 off of, and you're left with an x squared minus 2x plus 5. And to see if this even factors, because it's not going to factor nicely, I can totally tell, right? Two numbers that multiply to 5 and add to a -2, not happening. But to see if it factors some other weird way, we will use the quadratic formula. So x is equal to the opposite of a -2 plus or minus the square root of that negative 2 squared minus 4 times a times c all over 2a. You get this 2 plus or minus square root of 4 minus 20 or negative 16 all over 2. And that is, when you simplify this down, 2 plus or minus square root of 16 is 4i because the square root of negative 1 divided by 2. So you have two possibilities. X is equal to 1 plus 2i, or x is equal to 1 minus 2i, which means that the factors are going to be x minus 1 minus 2i and x minus 1 plus 2i. The zeros are 1 plus 2i and 1 minus 2i. The factors, you move everything over the left-hand side. So that big old polynomial that we had at the top, really terrible it looked like, can be now written as the following. There you have it. Now, if you count up the ultimate powers here, remember the original polynomial, I'll scroll all the way to the top, was a 10th degree polynomial. Now, if you scroll all the way back down to the bottom here, I have a power of x, I'm going to use green here, from this guy, a power of x from this guy, 3 powers here, 3 powers here, and 2 powers there. So 2 plus 3 is 5, plus 3 is another 8, plus 1 plus 1, that would be 10. 10 powers of x altogether, or a 10th degree polynomial. Yep, that works out. Something that looked terrible from the get-go, actually with some good luck there, wasn't too bad. Now, something that happened within that problem is called the conjugate zeros theorem. So here's the statement of the theorem, and before proving it, or instead of proving it, maybe we'll just look at the previous example. But if the polynomial has real coefficients, which by the way, our previous example had just real coefficients, not complex coefficients, but real coefficients. So no i's are allowed on the coefficients for this theorem to work. But if your polynomial has real coefficients, and if the complex number z, which is pretty typical, we use z for a complex number instead of x. So if z is a 0, then its complex conjugate, z bar, is also a 0 of your polynomial. Now, before proving this, if we want to, let's take a look at that last example. And you'll notice I had a 0 at x equals 1 plus 2i, and its conjugate, 1 minus 2i, was also a 0. Honestly, this just comes from the fact that when you reduce down using the synthetic division, you eventually get to quadratics. And when you use a quadratic formula, it's b plus or minus the square root of a number over 2a. And it's a negative b, I get it, but negative b plus or minus the square root of the discriminant over 2a. And so you're centering at negative b over 2a. Let me highlight that. And then you have a plus or minus business going on there, and that plus or minus wiggles by the same amount. So you'll center at 1, you go away in the positive direction by 2i, and in the negative direction by 2i. And that's just by virtue of having a quadratic equation and using the quadratic formula. And I originally was going to just kind of gloss over and skip this proof, but actually I think this would be good for you to see this proof. We're going to assume we have a polynomial with real coefficients. So we're going to assume the if part. There's actually a lot to the if part. So there's a lot we can assume. We can assume that our polynomial has real coefficients and that we have a complex numbered 0. So those are 2 things I'm going to write down. All right, so suppose that p is a polynomial with real coefficients and that z, which is an element of the complex number system, that's what that notation means, is an element of the complex number system, I'll highlight that, is a 0 of our polynomial. Well, what can you say just from that statement? Well, then p of z must therefore be 0. That should make sense to you. What we want to show is that p of z bar is also a 0. so that when we plug it into our polynomial, we also get 0 out. And a little note off to the side. Z is just a complex number, so it's a plus bi, and z bar is a complex conjugate, a minus bi. So let's go ahead and start performing some mathematics here. I'm going to give myself a little bit of room. And we start by taking our polynomial, general polynomial here, just like we did in the previous proofs, and we plug in z bar, the conjugate. So all I'm doing is taking this general polynomial, which is normally, and maybe I should write it up above so that you can see it. Normally, a general polynomial looks like this, right? A sub n x to the n plus a sub n minus 1 x to the n minus 1. Each time you add a term, you're just losing a power on your variable x, and you're also losing the index on a there. So you get to this and plus a sub 0. Rather than x, though, we're plugging in z bar. And that's why you see this notation right here. Okay, so that's what we have so far. Now, before I can go to the next step, I need to prove something off to the side. So we're going to do a little aside here. Being able to work with complex numbers is critically important. So we're going to go ahead and do a small aside. In this aside, we're going to say, let's suppose that we have two numbers, z1 and z2. And we want to multiply them together and then take their conjugate. And I want to prove to you that that's the same thing as having taken their conjugates first and multiplied them together. So we want to prove that. So it's a very actually fast proof. All you need to do is assign some letters to z1 and z2. So z1 is a complex number, so it's like a plus bi, let's just pretend. And z2 we'll call c plus di. And we'll multiply them together and then take their conjugate. So multiplying these together and then taking their conjugate, you will get the following. A times c, let's see, plus a times di, plus b times ci, plus b times di squared. You look at that and you say, that's an absolute mess. It sure is, actually. And this is equal to the conjugate. Still, we're sitting there. And I'm going to collect the terms without the i's to one side. By the way, remember, I squared here is a negative 1. So I'm going to collect the terms without the I together. So I'll get AC minus BD, because I squared turned that coefficient of BD into a negative 1. And then plus AD plus BC times I. So I collected the stuff with the imaginary number together, and I collected the stuff without the imaginary number together. Now I will take the conjugate of this statement. This is going to be AC minus BD, and then minus AD plus BCI. Okay, so now we have that done. Let's see, by the way, that I should say was Z1 times Z2 bar. Let's see what Z1 bar times Z2 bar would have been. Well, Z1 was A plus BI. We're going to take its conjugate, and we're going to multiply that by C plus DI, which is Z2, and we're going to first take its conjugate. So that'll be A minus BI, and this will be C minus DI. Let's go ahead and multiply them together. You get AC minus ADI minus BCI, and then plus BDI squared. Again, I squared, that is again just a negative 1. So collect stuff without the i's. So you get AC minus BD, again, because that BD coefficient becomes a negative 1. And then minus the quantity AD plus BCI. because all I did was collect the negative sign here and factor it out front. And notice this statement is the same as this statement. Hence, this is going to sound weird, but we say this stuff a lot when you get to calculus. The conjugate of a product is a product of conjugates. It sounds odd, I get it, but there you have it. So let's go back and do something magical here. Once we know that the product of a conjugate is the conjugate of products, which basically tells us if I multiply z bar by itself n times, I could have just multiplied z by itself n times and then taken the conjugate. And the same thing with the second term. Instead of taking z bar and multiplying it by itself n minus 1 times, I could have taken z and multiplied it by itself n minus 1 times and then taken the conjugate. So very small move, but super important, because now I'm going to do something that is somewhat not so obvious. This is the same thing as a sub n bar times z raised to the nth bar plus a sub n minus 1, again bar, z to the n minus 1, again bar, plus dot 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 all the way down the line until you get to a1 bar, z bar, plus a naught bar. Why is an equivalent to an bar? Well, remember, these coefficients, this is what the whole theorem relies upon. We've supposed that our polynomial has real coefficients. Pretend for a moment that our coefficient look like this, a plus bi. Now remember, our coefficients are real, so b is 0 here, right? But I just want to bring something to your attention. The conjugate of that number is a minus bi. Well, if b is 0, then the conjugate of a is still just a. It's just you're subtracting 0 instead of adding 0. So a bar, a real number, its conjugate is just itself. There you go. That is why we can get to this point. Now, there's another thing that I need to say. Isn't that a product of two complex numbers, a bar and z to the nth bar? And we've just proven that the product of conjugates is the conjugate of their product. So I can glue these together just like this. I'll zoom out a little bit more. A n z to the nth under the same conjugate bar plus a sub n minus 1 z to the n minus first, again under the same conjugate bar, plus so on and so forth down the line, all the way until you get to a1z, all under the same conjugate bar, plus a naught. It has its own conjugate bar. Lastly, there is actually another aside I could put in here, but I'm not really going to prove it. I'm just going to say it. So here's my second aside. If I have complex numbers, let's say z1 bar plus z2 bar, I can group them together as z1 plus z2 underneath the same conjugate. It's actually not too bad to prove this one. I might as well, right? So actually, I'll leave it to you. Prove this one. Just prove this one for yourself. It's actually a very easy proof. Just assume that z1 is a plus bi and z2 is c plus di. Trust me, this is true. So the sum of conjugates is the conjugate of their sums. Again, you have to kind of get used to that language. It happens in calculus a lot. So here's a sum of a bunch of conjugates. So let's go ahead and write them as a conjugate of all those sums. There you go. But that is the same thing as p of z conjugate, isn't it? This, let me highlight it, all this polynomial on the inside, that's p of z. And then you're taking its conjugate. But didn't we just say at the very beginning that z is a 0 of p? That is, p of z, whenever we see that picture, we can replace it with 0. Here is that picture. Whoops, I missed it. Here is that picture. Therefore, that picture we can trade out for 0, and the conjugate of 0 is just 0. And we have shown through a chain of equalities that p of z bar is equal to 0. That is, z bar is also a 0. And that's the proof, QED. Now, I think that's enough for this video. We have gone through some heavy work. The next video is dedicated to really doing examples. But you should note, all the theory we're going through right now, that high-level thought process and being able to critically think your way through these proofs is very important. This is college-level thinking and really the gateway to calculus, college-level calculus. You'll be doing proofs in calculus. So you really need to wrap your mind around these introductory proofs. Not that you should be able to prove everything here, but at least the one I just mentioned. Go ahead and try to prove that aside, that z sub 1 bar plus z sub 2 bar is equal to the conjugate of z sub 1 plus z sub 2. All right, I hope I didn't put you to sleep.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.